Hello everybody, welcome back to another video. In our second video in our Introduction to Mathematical Proofs series, we're going to consider the sum of the first n consecutive positive integers. In particular, we will consider the following sum. We're going to sum from I equals 1 to n of I. If we go ahead and just plug in some terms, we'll see that we're getting 1 plus 2 plus 3 plus ... plus n. So we're plugging in our index I equals 1, then I equals 2, then I equals 3, etc. We're adding all that up, and then our upper index is n, so that's where we stop. Now, what we'd like to do by the end of this video is come up with a formula for what this is in terms of n. So we want a formula in terms of n, the number of terms that we have. That's our goal. And not only do we want a formula in terms of n, we want to prove that this formula is correct. So before we do that, let's take a look at an example. I'll pan over to the side here. Consider the following sum. Consider 1 plus 2 plus 3 plus ... plus, and let's say I write it as plus 98 plus 99 plus 100. So we're adding the numbers 1 through 100. And notice I've got 3 terms on the left, 3 terms on the right, and that will be important here in a moment. Now, of course, one could just add up all of these numbers together. They could get some value, and it would work, but in order to add all these together, you need to perform 100 additions, right? So it's not quite very, or 99 additions, rather. But anyway, it's not so helpful because there's nothing special about the number 100 here. I want to be able to add up the first n consecutive positive integers, no matter what n is. N could be any number, any finite positive integer I want. So this isn't, being able to do this by just adding everything up isn't too helpful. We want something more general, something more abstract we can use. So here's the idea. We can pair up terms in the following way. We can say this is the same thing as 1 plus 100 plus, let me pan to the side a little bit more, 2 plus 99, so notice how I'm pairing things off, plus 3 plus 98. Now maybe I'll put plus ... I should probably end the sum somewhere. Let's say it ends with 50 plus 51. That's where the numbers are going to meet in the middle, so I will write that in. Okay, now let's take a closer look at this. Well, 1 plus 100 is 101. 2 plus 99 is 101. You probably guessed that for each of these pairs we're going to get 101. So I'll write that. Now, how many pairs do we have? Well, we're subdividing 100 integers into pairs, so we've got 50 pairs, or I should say 50, let's just say 50 summands, each equal to 101. So in order to calculate this sum, we can just say, oh, well, there's 50 101s, so this is the same thing as 50 times 101. And if you use a little bit of trickery, 50 times 101, you can do it in your head fairly easily by writing 101 as 100 plus 1, and then using the distributive property. This is 50 times 100 plus 50 times 1. And then that's just, what would that be, 5,000 plus 50, which is 5,050. So what we've just done is we've come up with a technique to evaluate a lengthy sum such as this in a systematic fashion, one that doesn't rely on us particularly computing all of these sums, but rather just noticing the pattern, and then noticing that there are 50 summands or 50 pairs of numbers that are each adding up to 101, so we can just take 50 times 101. So this idea is very nice, but we want something more general again. So from looking at this, maybe we can come up with a hypothesis for what our formula is. So let's think about this a little bit longer. We've got ultimately what we're doing in calculating 50 times 101 is remember how we got 50. We took 100 divided by 2. So this is like 100 divided by 2 times 101. And now remember, we wanted our formula in terms of n. So n here was 100, right? So perhaps the formula is n, that's 100, times 101, that's n plus 1, all over 2. Perhaps this is our formula. And if it is, we can prove it in a fairly straightforward fashion by what's called induction. So now we're actually going to go ahead and prove this by induction. So we want, maybe I'll type out, or I'll write up the conjecture. Our conjecture is that the sum from I equals 1 to n of I is just equal to the number of terms times the number of terms plus 1 all over 2. That's our conjecture. And what we'll do below is we will prove it. So let's pan down here. Let's make this the top of our page. And let's go ahead and prove this by induction. So I haven't made a video on induction yet, so this video may be a little bit new to people who've never seen induction, but that's okay. Maybe in a future video I'll go over the different kinds of induction and explain explain all of them in more detail. But for this video, let's just jump into it and try to follow what I'm doing. So in an induction proof, the first thing you always do is you have to prove what's called the base case. So we kind of prove what happens for the lowest value of n that we're considering. So let's consider the base case when n is equal to 1. So if n is equal to 1, is it true that the sum from I equals 1 to 1, right, because that's n is 1, of I, is it true that this is equal to what we get on the right-hand side? Well, for the sum from I equals 1 to 1 of I, that's just the number 1. So let's see, if we plug in 1 for n into this formula, if we compute 1 times 1 plus 1 over 2, on the right-hand side we check that we get the same value. We get 1 times 2 over 2, which is just 1. So we've established the base case. We've shown that this formula is correct when n equals 1. So in other words, another way of saying that is we've shown that P of 1 is true. Now the way general induction proofs work is you suppose, so this is our inductive hypothesis, inductive hypothesis. So now we suppose that P of n is true. So we suppose P of n is true, and then we want to show, in order to show that under that assumption that P of n is true, P of n plus 1 is true also. So basically, induction is kind of like a domino effect. If we show that the base case holds, and then we suppose that P of n is true, and we're able, from that assumption, to prove that P of n plus 1 is true, we have proven it by induction. That's the idea. because if P of 1 is true, then we can show that P of 2 is true. And if P of 2 is true, then we can show that P of 3 is true, and all the way up to n plus 1. So that's the idea. So anyway, we want to suppose that P of n is true in order to show P of n plus 1 is true. Well, P of n is the statement right here. P of n plus 1 would be basically what we get when we plug in n plus 1 for both the left-hand side and the right-hand side. We have to make sure that that it's true for both sides of this equation. So let me be a little bit more specific. So we suppose P of n is true. So this is just kind of general. So we suppose that P of n is true, which basically means we suppose, more specifically, we suppose that the sum from I equals 1 to n of I is indeed equal to n times n plus 1 over 2. And our aim is to show, we want to show that the sum from I equals 1 to n plus 1 of I is equal to what we get when we plug in n plus 1 for n. So I want to show that it's equal to n plus 1 times n plus 2 over 2. If we can show this, if we're able to show this equality, then we're done. And we are under the assumption that this is true. So here's what we can do. We can actually take this sum right here, and we can split it up into two sums. So down here, I'm gonna pan down. Down here, which is what I'm gonna write. I'm gonna write the sum from I equals 1 to n of I plus the sum. Maybe I'll write out the first thing first. Sorry. Let's write it out like this. This sum right here that we've circled is equal to the sum from I equals 1 to n plus the sum from I equals n plus 1 to n plus 1 I. So we're splitting it up into two pieces. The first piece is just summing up to n, so that's like what we've got up here, just summing up to n. And then the last sum is just what we get when we plug in n plus 1. So it's like up to n and then plus n plus 1. So let's write this in now. This is the same thing as the sum from I equals 1 to n of I. That's an I. Plus, and now we're substituting in n plus 1 where I is. And that's our only term in that sum, so we just get this. Now, what do we need to show? We need to show that this gives us this. If we use our inductive hypothesis and we simplify this, we should end up with this. And if we're able to show that, we are done. So let's use the inductive hypothesis now. The sum from I equals 1 to n of I is just n times n plus 1 over 2. And now we're adding n plus 1. Pan down. Let's find a common denominator here. That would mean multiplying the top and bottom of this expression by 2, which means we just end up getting n times n plus 1 plus 2 times n plus 1 all over 2. Now this is actually just equal to, let's think, well, we can factor out an n plus 1, right? And n plus 1 is in common between these two terms, so we can factor that out. And we get n plus 1 times, and then what's left over? We have n and then a plus 2. And then of course that's still all over 2. So let's pan out and maybe summarize what we've done, because we're actually done with the proof. Usually they'll use like a little box or something and fill it in when you're done with the proof, but whatever your convention, whatever you like to do for ending a proof, you could do QED. I don't know, there's lots of different ways to end proofs, but let's go ahead and zoom out and let's summarize what we've done. So we wanted to prove this summation formula right here. And we're proving it for these positive integers, so induction is a good way to go, generally speaking. So we took a look at the sum from 1 to 100, all those consecutive integers, and we found a pattern. And from that pattern, we were able to establish what we believe to be our formula. From our kind of our inductive reasoning using this pattern to give us our formula, we use induction to prove, pan out or zoom out here, prove our conjecture that the sum from I equals 1 to n of I is just n times n plus 1 all over 2. We approach this by induction. We prove the base case. Just the number 1 is the same thing as 1 times 1 plus 1 all over 2. We got 1 in each case, so we verified the base case. And we know that in general, for induction proofs, we just suppose that P of n is true after showing the base case, and then if we're able to show that P of n plus 1 is true after that, then we're done. So we suppose that P of n is true. We suppose that the sum from I equals 1 to n of I is n times n plus 1 over 2, with the ultimate goal to show that P of n plus 1 is true, that the sum from I equals 1 to n plus 1 of I is n plus 1 times n plus 2 over 2, which is just from plugging in n plus 1 where n is in this expression. So we considered that sum that I've circled here, the sum from I equals 1 to n plus 1, and we split it up into two different sums. One sum is just the sum given by our induction hypothesis, and the other sum is just that final term that we're adding on. So we just have from I equals n plus 1 to n plus 1. You know, notice there's only one term in the sum. We plug that in to get n plus 1. We utilized our inductive hypothesis here, found a common denominator to see if it simplified nicely to something that would be what we want to show. And after factoring, it turns out that it was. So we did, in fact, prove that the summation of the first n consecutive positive integers is indeed given by this formula. So I hope that you've enjoyed this video. It's a little bit longer than I had originally intended, but I suppose that introducing induction, all of these things does take time. So anyway, that's it for this video. In a future video, we'll take a look at another proof, perhaps another induction proof, perhaps something else. I'm not sure yet, but anyway, stay tuned, and I'll see you all in a future video.